Hello everyone, in this video lecture we are going to see how to analyze indeterminate beams by stiffness matrix method. So for this we are taking this example. Okay, so analyze the two span continuous beam ABC with the overhang CD as shown in figure by stiffness matrix method. Draw the shear force and bending moment diagram. This is our example. So we know stiffness matrix method comes under displacement method. Okay, so in the displacement method we are treating displacements are unknown. Okay, like rotations and translations of the joints are treated as unknown. Okay, so therefore in the first step, okay, so in the stiffness matrix method, what is our first step means first we need to determine degree of freedom of this structure. Okay, first we need to determine degree of freedom. So in this structure, so what should be the value of degree of freedom? Okay, so for this we are neglecting axial deformation. Okay, so we are neglecting axial deformation. The members, the beams are axially rigid, so we are neglecting axial deformation. Now determine the degree of freedom for this structure, degree of freedom. Okay, so for this consider joint A. So the joint A, it is a fixed end. Okay, so at the fixed end it offers resistance against both translation and rotation. So therefore degree of freedom at joint A is equal to 0. Then joint B, it represents a roller support. So at the roller support we have 2 degree of freedoms are available. Generally 2 degree of freedoms are available. So one is rotation, then another one is horizontal translation. So in this case we are arresting axial deformation, that is we are neglecting axial deformation means we should consider only one unknown, that is a rotation of this joint B. Okay, that is a rotation of joint B. Then again joint C, it is a roller support. At the roller support we have 1 degree of freedom, this is theta C. Then at the free end D, we have 2 degree of freedoms are available. Okay, so generally 3 degree of freedom is available. One is horizontal translation, delta x, then delta y, then rotation. Okay, but in this case we are neglecting axial deformation, that is we are neglecting this delta x. So therefore at the free end we have only 2 degree of freedom, that is theta d and delta yd, delta vd. Okay, so therefore, so how many degree of freedoms are available? 4 degree of freedoms are available. So one is theta b, then theta c, then theta d, then delta vd. Okay, vertical displacement at the free end. Okay, so 4 degree of freedoms are available. So 4 degree of freedom available means our matrix is in the form of 4 by 4 matrix. It is very difficult to solve by manually. So therefore what we do means we are simplifying the structure. Okay, so we are simplifying this structure. So the overhanging portion being a determinate portion, so we know this overhanging portion CD portion, it is a determinate one. Okay, so overhanging portion is a determinate portion, so it may be dropped from an indeterminate structural analysis after accounting its effect on the rest of the beam. Hence beam considered for the analysis is shown in figure below, in which the cantilever moment is the fixed end moment at a C. Okay, so we know this is a cantilever portion, so that is overhanging portion is a determinate one. So therefore we should drop it, with the dropping of this cantilever portion means you can reduce 2 more unknowns. Okay, so that is at the free end of the cantilever. So one is theta d, another one is delta vd. So 2 degree of freedoms are available. If you are neglecting this portion means you can decrease the number of unknowns. Okay, so we are decreasing number of unknowns. If number of unknowns decreased means our matrix size also decreases. Okay, so therefore we can drop that overhanging portion, but its effect should be accounted. Okay, so its effect, so it induces this overhanging portion induces the moment of 20 into 2, 40 kilometer meter at the end C. Okay, so therefore this is our modified structure. Okay, so this is our modified structure. So now determine kinematic indeterminacy of the structure. Okay, so kinematic indeterminacy of the structure, so dk is equal to kinematic indeterminacy or degree of freedom of the structure. Dk is equal to 3j minus r minus m. So in this structure, this modified structure, we have 3 joints A, B, C, then number of unknown reactions of 5. Okay, so at the fixed end 3 reaction, at the roller in B we have 1 reaction, then at C also we have 1 reaction. Totally 5 reactions are there. Then how many members are there? 2 members. One is AB member, another one is BC member. So number of members is equal to 2. Then substitute J or M in dk equation, you get kinematic indeterms is equal to 2, that is theta b and theta c are the two unknowns, 2 degree of freedoms. Or you may use this method. Okay. So, at the fixed end that is offers resistance against both the translation and rotation, therefore, degree of freedom at the end A is equal to 0, then at B only theta b is not equal to 0, other two displacements 0. Then at the end C, so at this end also theta c is not equal to 0, other two displacements is equal to 0. So, finally, you get a kinematic indeterms is equal to 2, that is theta b and theta c. Okay. So, this is our first step. Then second step is assign one coordinate in the direction of each unknown displacement. Okay. So, we have selected unknown displacement. Okay. So, degree of freedom for this structure is 2. So, it is theta b and theta c. Now, we are going to assign one coordinate in the direction of each unknown displacement. Okay. So, therefore, for theta b we are providing coordinate 1. Okay. So, it is a rotation coordinate. Okay. So, like moment 1. Okay. So, moment 1, then theta c also it is a second one. Okay. So, this is first one, theta b is first unknown, theta c is second unknown. So, in this unknown displacement direction we should provide some rotation. Okay. So, some coordinate we should assign the coordinate. Okay. So, 1 and 2. Then in the third step restrain or lock the complete structure. Okay. Restrain or lock the complete structures and find out the force developed in the restrained structures in the coordinate direction. Okay. So, in the third step what we have to do means we should restrain entire structure, that is assume all the ends are fixed end. Okay. So, all the nodes are fixed end. Then find out the force developed in the restrained structures in the coordinate direction 1 and 2. Okay. So, our coordinate direction 1 is it is at a B. Okay. At a B end, B joint, then coordinate 2 is at a C joint, both are moment coordinate. Okay. So, our unknown is theta b. So, therefore, we are providing moment coordinate. Okay. So, first consider AB portion of beam. Okay. So, consider AB. Okay. So, in this case only we are assumed it is a restrained structure, we assume both the ends are fixed. So, in the AB portion which is subjected to some external moment, okay, external force UDL, its value 40 kilonewton per meter, its length 4 meter. Okay. So, due to that external force, external transverse force, you may get some end moment, fixed end moment. Okay. So, its fixed end moment M of AB is equal to minus WL square by 12, then M of BA also WL square by 12. Okay. So, left hand moment M of AB moment is an anti-clockwise moment and M of BA moment is a clockwise moment. M of AB anti-clockwise moment, M of BA is a clockwise moment. Okay. So, substitute W is equal to 40 and L is equal to 4. You get minus 53.33 for M of AB, then plus 53.33 for M of BA. Okay. Then consider second span BC. Okay. Consider second span of BC. So, this is B, this is C, its distance between B and C is 4 meter. Okay. So, in this beam, okay, in this portion of beam there is no external force. So, therefore, the end moment is equal to 0, that is M of BC and M of CB both are equal to 0. Okay. So, do not consider this one. Okay. So, we are considering only transverse loading, consider span AB then span BC separately. Okay. So, individually consider span AB and span BC. So, assume both the ends are fixed. Okay. So, we are considering restrained structure. So, restrained structure means it offers resistance against both translation and rotation, that means our both the ends are fixed end. Okay. So, our both the ends are fixed end. So, consider AB, it is subjected to some transverse load UDL. So, due to that UDL you get a moment minus WL square by 12 on the left hand, on right hand it is plus WL square by 12. Then BC portion there is no external force, its moment end moments are 0. Okay. So, in this term what we need to determine is force developed in the restrained structures in the coordinate direction. Okay. So, therefore, we need to determine a moment at the coordinate direction 1 and coordinate direction 2. Okay. So, what is our coordinate direction 1? So, coordinate direction 1 is at joint B, then coordinate direction 2 is at joint C. Okay. So, at the joint B, so it is a junction of two members. Okay. So, So, it is a junction of two members, one is BA member, another one is BC member. So, therefore, moment induced in the first coordinate in the restraint structure is equal to m of BA plus m of BC. Then moment induced in the restraint structure at the coordinate direction 2 is equal to, so only m CB. Okay. So, determine its value. So, m of BA we know it is 53.33, m of BC is 0. Okay. So, you get 53.33 in the coordinate direction 1. Okay. So, you get a force of 53.33 kilonewton meter. Okay. So, force in the sense it includes both point load and moment. Okay. So, therefore, generally we use the term force. Okay. So, in the coordinate direction 1 we get a force of 53.33 kilonewton. Then in the coordinate direction 2 P2 is equal to, it is 0, MCB is equal to 0. Okay. So, P1 dash equal to m of BA plus m of BC, then P2 dash is equal to m of CB. Okay. So, P1 dash is equal to 53.33, then P2 dash is equal to 0. So, it may be represented in a matrix form, it is a column matrix. Then in the fourth step, remove the given external force. Okay. Remove the given external loading, and supports and joints are released or unlocked. Okay. Supports and joints are released or unlocked by permitting deflection at the assigned coordinate. Okay. So, now we are going to now we are going to remove all the external load and permit deflection at the assigned coordinates 1 and 2 separately. Okay. So, first we allow a rotation at the joint 1, then we allow rotation at the joint 2. Okay. Then find out the force developed in the released structures in the coordinate direction. Okay. So, first thing we need to allow a rotation at the joint B. Okay. So, due to that rotation, what is the force developed in the released structures? We need to determine force developed in the released structure. Then allow second rotation. Okay. Second rotation, again determine force developed in the released structures in the coordinates. Okay. So, this force is represented by P suffix delta. P suffix delta matrix is equal to, so stiffness K matrix times delta matrix. Okay. So, we know stiffness matrix, in our case we have only 2 degree of freedom. Okay. So, only theta B and theta C. So, therefore, the order of the matrix is equal to number of degree of freedom. Okay. So, order of the matrix is equal to number of degree of freedom. So, our case, so we have only 2 degree of freedom. So, therefore, our stiffness matrix is a 2 by 2 square matrix. Okay. So, its ordinates, okay, ordinates of elements of the stiffness matrix is equal to K11, K21, then K12, K22. Okay. Then displacement matrix. Then displacement matrix is equal to first theta B, then theta C. Okay. So, it may be written as delta 1, delta 2. Okay. So, it is represented in a column matrix. Okay. So, P delta. Okay. So, this is the force developed in the released structure. Okay. So, in the fourth step, what we have to do means we are removing all the external load. What we are doing means we removed all the external force, then released or permitting. Okay. So, released or unlocking the joints by permitting deflection at the assigned coordinate. Okay. So, our assigned coordinate one is theta B, then second one is theta C. Okay. So, its force P delta is equal to K into delta. So, for this we know this delta matrix is equal to theta 1 by theta 1, theta 2, but we do not know the value of stiffness matrix. So, for this we need to develop stiffness matrix. So, for this first we need to develop the first column of stiffness matrix. Okay. First column of stiffness matrix. For this we need to permit unit displacement in the coordinate direction 1. Okay. So, all other coordinate directions are locked, only we need to apply unit displacement in the first coordinate direction. So, that is, so initially what we assume means all the ends are fixed end. Okay. So, all the ends are fixed end. So, A end fixed, then B end fixed, then C end fixed. Now, what we have to do means we are permitting some rotation. Okay. So, we are permitting some unit displacement at the assigned coordinate 1. So, what is our assigned coordinate? It is the rotation. Okay. So, theta B is our assigned coordinate 1. So, we are permitting theta B is equal to 1 in this structure, that is we are permitting rotation at a node B. Okay, so we are permitting rotation at node B. So therefore it may deflect this way. Okay, so we are permitting some rotation, theta B is equal to 1, theta B is equal to 1. Okay, so B, it represents a junction of two joints. So therefore draw the separate figures for AB portion and BC. Okay, AB and BC, draw the free body diagram for this. Okay, so consider this is AB. So initially both the ends are fixed. We are permitting one unit rotation at B, one clockwise unit rotation at B, theta B is equal to 1. Okay, so for this structure on the, due to that rotation you get some end moment. Okay, so we are permitting some rotation, due to that rotation you get some end moment. Okay, so at the joint B you get a end moment of 4 EI by L, this is the general formula. Okay, then in this end you get 2 EI by L. So in our case, so EI for this beam AB is 2I. Okay, so substitute I is equal to I, then length is equal to 4, length is equal to 4. Okay, so therefore at this end, at the end A you get a moment of EI, at the end B you get a moment of 2 EI. Then consider second part of the beam. Okay, so that is BC beam. So again permit unit rotation at a joint B. Okay, so joint B. So again you get a moment 4 EI by L at the end B, that is MBC moment. Then MCB moment is 2 EI by L, both are in clockwise direction. Okay, if rotation permitted in clockwise direction means the end moment, both the end moments are in clockwise direction. Okay, so therefore the stiffness K11. Okay, so stiffness K11 means, so force developed in the direction of first coordinate due to unit displacement applied in the first direction. Okay, so it is at what location, it is due to which displacement. Okay, so K11 is equal to, so our assigned coordinates. Okay, so K11 stiffness 11 K11 is equal to moment by rotation. Our assigned coordinate is a moment coordinate. Okay, so moment 1. Okay, so stiffness is equal to moment by rotation, which is equal to, so which is equal to moment at joint B. Okay, so it includes the moment of MBA and MBC. Okay, so at MBA and MBC, so this is K11, so its value 3 EA. Then K12, so K12 means force developed in the second coordinate direction due to unit displacement applied in first coordinate direction. Okay, so in the first case we are applied only unit displacement in the first coordinate axis. So due to that unit displacement you need to determine the forces at the first and second coordinate, which forms the stiffness matrix. Okay, so which forms the first column of our stiffness matrix. Okay, so K22 is equal to, so moment developed at the second coordinate direction. Okay, so its value is equal to 2 EI by L. Okay, so 2 EI by L, it is 4, you get EI by 2. Okay, so this forms the first column of our stiffness matrix, 3 EI, then EI by 2. Okay, then in order to develop the second column of stiffness matrix, now we need to apply unit displacement in the coordinate direction 2 only. Okay, so all other coordinates are fixed. Okay, so all other coordinates are fixed. For developing second column of stiffness matrix, you need to apply unit displacement in the coordinate direction 2. Okay, so our coordinate direction 2 is moment coordinate at a moment or rotation coordinate at joint C. Okay, so now we are permitting unit rotation. Okay, so unit rotation at a joint C. Okay, so theta C is equal to 1. So all other ends are fixed. We are assuming all other ends are fixed. Okay, so due to that rotation you get a end moment, MCB end moment is equal to 4 EI by L, MBC end moment is equal to 2 EI by L. Okay, so first consider BC portion of beam. So sorry, first consider AB portion of beam. So AB, so this end is fixed, this end also fixed. So there is no rotation, there is no translation, there is no external force. Okay, so in this case this is end A, this is end B, its length and the sum L. So there is no rotation. Okay, theta A is 0, then theta B. So in this case we are permitting rotation at joint C, that is theta C is equal to what? All other rotations are 0, theta B also 0. Okay, so therefore the end moments are 0. Okay, so MBA is equal to 0, sorry, MAB is equal to 0, then MBA also equal to 0. So this is for first span. Then second, consider second span. So this is B, this is C. Okay, initially it is fixed, but we are permitting some unit rotation, unit clockwise rotation at this joint C. Okay, so rotation is equal to 1. So due to that clockwise rotation, you get an end moment in clockwise direction. So both end moments are clockwise direction. Its value MCB is equal to 4 EI by L, MBC is equal to 2 EI by L, MBC. Okay. Then again determine K12, K22. So K12 means force developed in the direction 1 due to unit displacement given in direction 2. Okay. So our assigned coordinate is a moment coordinate. So therefore you need to concentrate a moment at a joint B. Okay. So at the joint B it is a junction of two members. So one is MBA, another one is MBC. Okay. At these two moments, we know MBA is equal to 0, MBC is equal to 2 EI by 4. Okay. So substitute K12 is equal to 2 EI by 4. Then K22. So K22 means force developed in the direction 2 due to unit displacement given in direction 2. Okay. So its value is equal to 4 EI by L. Okay. So therefore our stiffness matrix. So second column of our stiffness matrix, EI by 2, then EI. This represents second column of our stiffness matrix. Then finally our stiffness matrix is equal to, so first column is 3EI by 3EI and EI by 2, in second column EI by 2 and EI. Okay. So it's a 2 by 2 square matrix. Okay. So therefore the force developed and the release structure is equal to P delta is equal to K into delta. Okay. So P1 delta, so P delta it is represented as a column matrix. So it is P1 delta, P2 delta equal to 3 EI, EI by 2, EI by 2, EI into delta. Deltas are theta 1 and theta 2, that is theta B and theta C. Okay. So in the fifth step, the final force in the direction of assigned coordinate will be, final force in the direction of assigned coordinate will be, so total P, final force P matrix is equal to P dash matrix plus P delta matrix. Okay. So P dash matrix plus P delta matrix. So this thing we already determined, P dash matrix. Okay. So is the end moment and the for the restraint structures. Okay. Then the final force. So final force means, so it represents any external force acting at the joint. Okay. So it includes any external force directly acting at the joint. So our case, so our modified beam is like this. So this is our modified beam. Our assigned coordinate, what are our assigned coordinates? Joint B and joint C are our assigned coordinates. Both are a clockwise moment. Okay. So our assigned coordinate on the one is a clockwise moment. So this one also clockwise moment. Okay. So in the final force means, for a external system. Okay. So for a initial case, is there any moment is there at a joint A, joint B and joint C. Okay. So in this case on the joint B there is no external moment at a joint B. Okay. So therefore this M1 force is equal to 0, then M2 force is equal to 40. Okay. So we have 40 kilonewton force, it is a clockwise moment. So it represents the external force. Okay. So its value 40. Okay. So therefore the final force is equal to M1 by M1 M2. Okay. Which is equal to 0, 40. Therefore P, the final force is equal to P dash plus K into delta. So delta we need to determine this delta value. So these are our unknown. Okay. So initially we treat a degree of freedom is our unknown. So we need to determine its value. Okay. So for this delta is equal to displacement matrix is equal to K inverse P minus P dash. Okay. So we know delta matrix is equal to, that is displacement matrix is equal to rotation 1 rotation 2. which is equal to stiffness inverse final force minus P dash. Okay, so substitute all the values, you finally get theta B is equal to minus 26.67, theta C is equal to 53.33. Theta B is equal to 26.67, theta C is equal to 53.33. So, we know theta A is a fixed run, so theta A is equal to 0. Then there is no sinking of support, delta 0 also 0, sinking of support is not there, so therefore delta is equal to 0. Then finally we should determine end moment, final end moment. Okay, so this final end moment is determined from general slope deflection equation. So, we know general slope deflection equation, that is MAB moment is equal to MFAB plus 2EI by L into 2 times theta A plus theta B, then minus 3 delta by L. Okay. So, substitute MFAB, we know its value. Okay, so it is already determined. Then 2EI by L, then theta A is equal to 0, theta B is equal to, we know its value, then delta, there is no sinking of support, therefore this delta equal to 0. So, substitute these values, you get a end moment, final end moment. Likewise, you get MBA moment, then MBC, then MCB, NCB moment. Then finally draw the bending moment diagram with the help of these end moments. Okay. So, our final end moment diagram, it is a superimposed bending moment diagram. Okay. So, superimposed bending moment diagram. So, it includes negative moment and positive moment. So, we determine negative moments, that is MBA, MAB, MBA, MBC and MCB. Okay. So, MAB moment is minus 40, MBA is equal to 0, then MBC is equal to minus 40. Okay. Then we are imposing simply supported moment also. Okay, so this simply supported moment, that is span moment is equal to, so if it is subject to uniform distributed load means its value WL square by 8. Okay, so put W and L and 8 means you get the its moment. Okay, so this represents the final bending moment diagram. Thank you.